Right. So, let us now establish the basic equations of magnetohydrodynamics, and since we are going to be dealing with electric and magnetic fields, yes, we did say that electric fields are technically 0 inside of a fluid, but nonetheless we have to start with them and then show that they reduce to 0, right. And so since we are talking about electric and magnetic fields, we have to deal with Maxwell's equations, right. And so these are the 4 Maxwell's equations, these are the 2 divergence equations. This is essentially saying that the divergence of B is 0, in i.e. there are no magnetic monopoles, that is what this equation is saying. No magnetic monopoles or magnetic field lines are always closed. This is essentially saying that establishing the relation between okay, here sigma is not conductivity, sigma is, this is charge density. I beg your pardon for the change in notation, but normally we will use sigma for conductivity, but in this particular equation it is charge density. So, this is telling you how the electric field is related to charges, right. And so, these are the 2 divergence equations, and this is telling you how a changing magnetic field produces an electric field, and this is telling you how a changing electric field produces a magnetic field. And so, this would be, this is essentially the displacement current term, and this would be the physical non-displacement current part of the current, if you will. Okay. So, that is the displacement current and this is the non-displacement current. Taken together, this the left hand side here would comprise the charge density, the current density, and the right hand side is the curl of B. And I must emphasize that all of these equations are written in CGS. Okay. That is why you see the appearance of C like the speed of light. Okay. If you are writing this, you might you can equivalently write these things in SI units. It is just that these constants will appear slightly different. If you are more comfortable with SI units, that is fine, no problem. The basic physics is still the same, but I wanted to emphasize that these 4 equations, the Maxwell's equations, are written in CGS units. Okay, right. So, now let us take the divergence of the first equation of this equation. Right. So, let us take the divergence of this equation. In other words, I operate this entire equation by like that. Right. So, I have the divergence of J, which is that, right, and the divergence of, well, this would essentially become d over dt of the divergence of E. I am assuming that the time and space derivatives can be interchanged, and for the divergence of E I substitute from here, right. For this one I substitute from here. Okay. And the divergence of a curl is always 0. So, therefore, this term taking the divergence of the right hand side just gives you 0. So, taken together, taking the divergence of the first equation gives you what is called the charge continuity equation, okay, which you must, which you are familiar with from basic electrodynamics. This is essentially saying that the divergence of the current density is equal to the time derivative of the charge density. Okay. If there is no current flowing inside or out of a volume through the surface, there is no way the charge density inside that volume will be changing with time. That is what this equation is saying. You can also think of this as the equation for conservation of charge. Charge is always, electric charge is always conserved. That is what this equation is saying. Okay. So, that is one thing. And now to deal with that all important electric field. We made a big fuss about the electric field. Remember, we kept saying that the electric field in the fluid frame is equal to 0. So, let us deal with it. Okay. All right. So, firstly, the fluid is supposed to be infinitely conducting, right. The conductivity is infinite, therefore, there is no way you can have an electric field inside of the fluid. There is no way you can have an electric field in the quote unquote fluid frame. That is not possible. Okay. Right. So, okay. So, but what about an external observer's frame? What about an observer, i.e., an observer who is outside the fluid? What about this kind of observer? Okay. Okay. So, it's clearly the way we are talking about this, we are implying that the electric field need not always be 0 for someone who is not immersed in the fluid. The electric field has to be 0 for someone who is immersed in the fluid, simply because the fluid is infinitely conducting. But in order to answer this question, we have to resort to a standard Lorentz frame transformation, and that is this. Okay. So, the primes would denote the fluid frame. Okay. So, and we have a parallel and perpendicular. In other words, what we are going to do is, you have, suppose you have two frames, one a fluid frame and one is an observer's frame. Okay. And the fluid frame has primes in it. So, wherever you see primes, E prime, B prime, and so on and so forth, you are in the fluid frame. The primes denote the fluid frame. Okay. And say, just for concreteness, this is the x axis. So, this would be the x prime. Okay. And this would be the x axis here. So, this would be the observer frame, the external observer frame. And the main thing is, the external observer is moving with a velocity v with respect to the fluid frame, and that is how you make the transformation. So, the parallel refers to parallel to v, and perpendicular refers to perpendicular to v. Okay. And for simplicity, we have taken in this particular way of doing things, we have taken v to be parallel to the x axis. Okay. This is no loss of generality, because even if you wanted to treat v, some other v, you would just split up the components, that is all. Okay. The basic results are exactly the same, right. So, now this is the Lorentz transformation of electromagnetic fields. Lorentz transformation, okay, which is relating the fields in the fluid frame. In other words, the frame and all quantities in the fluid frame have a prime on top of those, like this, and all quantities in the non-fluid frame, in the external observer frame, which can potentially be moving with respect to the fluid frame. Okay. Those do not have primes. Okay. And the parallel denotes parallel to the velocity of movement, and perpendicular denotes perpendicular to that direction, right. And this is essentially how you transform between these two frames, and this is called Lorentz transformation. The E parallel prime is the same as E parallel. However, that is not the case with E perpendicular. And this gamma is essentially, you see this V here, the gamma is essentially the Lorentz factor, and the gamma is defined as 1 minus V squared over C squared raised to minus 1/2. Like that. Okay. Maybe I should erase this and write it again. Yeah, well, it's a little difficult. This is essentially 2. Okay. So, gamma is 1 over square root of 1 minus v squared over c squared. Okay, so that is what this gamma is. It is essentially v, it is a function of v. Okay, c is the velocity of light. Okay, and so the E perpendicular prime is not the same as E parallel E perpendicular. There is this v cross b business sitting in here. And however, so the B parallel prime is the same as B parallel. So as far as the parallel components are concerned, that both the electric field and the magnetic field, they are unaffected. It's only the perpendicular components which are affected. So this is how you transform between the primed frame and the unprimed frame. Okay, right. So let's keep this in mind. Now we know that all primed electric fields are 0. Right? There is no electric field in the fluid frame, in the primed frame. There is no electric field. So E parallel prime is 0. So therefore, E parallel is also 0. For that matter, E perpendicular prime is also 0. Okay. So in other words, E parallel prime is equal to 0 and E perpendicular prime is also equal to 0 by definition. Therefore, you get, so E parallel, this is already 0, just so directly from here you get this. This is very interesting. Okay. So the quantity in the brackets is equal to 0 and that just gives you this. So now pay close attention, this is the electric field not in the fluid frame, that is always 0, but this is the electric field in the external observer's frame. And that is non-zero, that is related to the magnetic field that the external observer sees in this manner. Okay. And note, we usually deal with non-relative MHD. There is such a thing as relativistic MHD, but generally speaking we deal with non-relativistic speeds in MHD, and therefore V over C is much smaller than 1. So even in the non-primed frame, even in the external observer frame, because V over C is much less than 1, the bare magnitude of the electric field is very small. In comparison to what? Well, the magnitude of the magnetic field, for instance. So what does that say about electric fields? Electric fields are technically 0 in the fluid frame and even in the external observer's frame, because we are restricting ourselves to non-relativistic speeds, even in the external observer frame, the electric fields are pretty small. Okay. So this is something to keep in mind very firmly, right? So this was a brief detour into the role of the electric field in MHD. Okay. And this is about it. We will not be talking too much about electric fields anymore. As we said, we will mostly be encountering magnetic fields from now on, not mostly, exclusively. Okay. And this is why. Okay. Before going ahead, it is important to be very clear about the details, and this is why you do not worry about electric fields at all in MHD. Okay. Right. So now, using this fact that we just derived, E equals minus V cross B over C, what we do is we use this in Faraday's law. In the Faraday, so you have the curl terms were Faraday's law and Ampere's law, right? So in the basic Maxwell's equations that we saw, this was Faraday's law. And this is Ampere's law. Right. So what we are going to do now is substitute for the E that we found inside Faraday's law. Okay. So we are going to use E equals minus V cross B over C in Faraday's law, right. So, to eliminate this E in order to get what is called the induction equation, which gives you the time evolution of B. There is only B you see in this equation, there is no E at all. Okay. So, this given a certain velocity field, this tells you how the magnetic field evolves. Okay. That is what this equation is telling you. Given a velocity field V, this tells you about the evolution of the magnetic field, the time evolution, the time evolution of the magnetic field B. You see the time evolution. All you need is V, right, and this gives you, this is a complete dynamical equation for B. Okay. And this is what is called the induction equation. It is very, very basic in MHD, and many times when you see the equations of MHD written down, they just start from the induction equation, assuming that you know, right. So, it is important to know where the induction equation came from, and this is where it comes from. Okay. It describes how a magnetic field evolves in response to a magnetic to a velocity field V, of course, in a perfectly conducting fluid. Why a perfectly conducting fluid? Because this whole thing, this thing applies only to a perfectly conducting fluid, E equals minus V cross B over C. If a fluid is not perfectly conducting, this does not apply. Okay. So, as such, the equation as it stands applies only to a perfectly conducting fluid. However, we will not derive this, but we will say this, in the presence of finite conductivity, in other words in the presence of dissipation, and we will not derive this, the induction equation has this extra term. This is an extra term. Where this lambda is related to the conductivity sigma c. This is the conductivity. Okay. So, you have the conductivity in the denominator here. Okay. So, this term in blue gives you the effects of finite conductivity or finite resistivity, however you choose to look at it. Okay. If you did not have this term, if the conductivity is infinite, then this lambda would tend to 0 and you would have the plain vanilla induction equation. And we derived this induction equation, we did not make any attempt to derive this extra piece, I am simply stating this. Okay. Right. The second term contributes simply to the decay of magnetic flux, the second term in blue. We will see how. Yeah. Now, just like we did dimensionless numbers in fluid mechanics, you know, and we did make some mention of the dimensionless numbers in magnetohydrodynamics, but here is the first time we are considering them explicitly. And so, let us see here. The first term you see, this guy, the first term on the right hand side, I must say, first term on the RHS. This guy is some kind of V times B, and this curl is a differentiation, right. So, it is a d over dx kind of thing. So, you have, so the d over dx can be some, I mean, you know, approximated by 1 over L, right. So, this first term is order V B over L. The second term is of order, what we do is we do not bother about the dimensions of lambda, we keep lambda as it is, right, and the B as it is, and since this is a del square, this would be something like a d square over dx square, and therefore, that is represented by L square here. Okay. So, the first term is order VB over L, the second term is of order lambda B L square, lambda B over L square. And the ratio of these two numbers, the ratio of the first term to the second term is called the magnetic Reynolds number, very similar to the fluid Reynolds number that we talked about earlier. And the magnetic Reynolds number is given by L times V, this divided by this, order of magnitude. LV, where L is some macroscopic length, V is some macroscopic velocity that we are talking about, say the fluid flow velocity, which of course has to be non-relativistic, okay, divided by lambda. So, for an infinitely conducting fluid, lambda is technically 0. You see the sigma c appears in the denominator, so and this is the conductivity. Right. So, lambda is technically 0. So, for an infinitely conducting fluid, since this is 0, the magnetic Reynolds number shoots up to infinity, right. And for a highly resistive fluid, where the conductivity is very finite, where it is large and therefore lambda is small, the magnetic Reynolds number conversely is small. So, infinite conductivity, infinite magnetic Reynolds number, that is how it goes. Okay. It is somewhat like, you know, 0 viscosity, fluid's Reynolds numbers went to infinity. You remember that, right? Fluid Reynolds number was LV over nu, where nu was the coefficient of viscosity. If the fluid was inviscid, then the fluid Reynolds number went to infinity. Here, if the fluid is infinitely conducting, then the magnetic Reynolds number goes to infinity. We made this comment here saying that the second term, this term, contributes to the decay of magnetic flux. Let us justify this. Consider, for instance, just the dissipative term. In other words, we will not bother about this term, we will only bother about an equation that has this term and this term, okay, which is like this: dB dt equals lambda del square B. This is a standard form for the diffusion equation. This is a diffusion equation. This is like, you know, in one dimension, for instance, this would be something like dB dt equals lambda d square B dx square, right. This is a diffusion equation, isn't it? And the solution to a diffusion equation is well known. So like that, okay. U x x is d square u d, where I say u t is du dt, and u x x is d square u dx square. That is a notation. Okay. So, this is a standard diffusion equation, and the Green's function for this, the Green's function is just, you can think of the Green's function as a response to a delta function excitation. Okay. In other words, the solution for at time t equals 0, you have a delta function injected into this, and you want to see how this excitation proceeds with time. That's what the diffusion equation is going to tell you, and the solution is this. So, you have a broadening decaying exponential. So, this would be decaying Gaussian, actually. It is something like this. You have time on the x axis, right. You started out with a delta function like this, and with increasing time, what you are saying is the variance increases and the height also, the height decreases. With increasing time, the height is decreasing and the variance is increasing, right. So, you started out with a delta function at time t equals 0. At a later time, it would look like this. And what does this represent? This represents the magnetic field. At a still later time, it looks like this. In other words, you started out with a point like magnetic field, as time progressed, what happens was the magnitude of the magnetic field decreased and it broadened, and as time progressed even more, the magnitude decreased even more and it broadened even more. And what is this? This is essentially saying that the magnetic field is spreading out, is diffusing. Okay. So, an initial delta function turns into a Gaussian that gets shallower and broader with time. So, the initial magnetic field dissipates away due to the effect of the finite conductivity, and the effect of the finite conductivity is all embodied in this lambda term, right. So, if there was no if the conductivity is infinite, then this term would not be there and the magnetic field would not diffuse away, it would not dissipate away. So, that is what that is why we made that statement in the previous slide. So, and so this would be a low Reynolds number situation. You remember Reynolds number, the magnetic Reynolds number was defined as LV over lambda. When the conductivity is finite, and that would mean that lambda is essentially small, and lambda is large, and therefore the magnetic Reynolds number is low. Okay. So, this situation low is typical of lab situations. Low magnetic Reynolds numbers are typically found in lab plasmas, whereas high Reynolds number situations are typical of astrophysical situations. In astrophysics, we typically deal with high magnetic Reynolds numbers. Okay. And if you remember the several examples that we discussed regarding fluids in astrophysics, accretion, even shock propagation, supernovae, so on and so forth. In astrophysics, we were also mostly considering high fluids Reynolds numbers. Okay. And as we are saying here, the magnetic Reynolds numbers are also very, very high in astrophysical situations. So, in other words, in astrophysical situations, the fluid Reynolds number also tends to infinity. Okay. So, both the magnetic Reynolds number and the fluid Reynolds number in astrophysical situations are very high. So, this is something to keep in mind. There are many caveats to this statement though. Although the statement is generally taken to be true, one should accept it only with a grain of salt. I just wanted to make that clear. So, there are some consequences from the induction equation. So, if we take the conductivity to be infinite, in other words, if we take this term to be essentially 0, in other words, if we take the magnetic Reynolds number to be technically infinite, you only have this, the induction equation is just this, right. What you do is suppose you take its divergence, you take the divergence of on both sides, right. So, you take just this, of this whole thing, right, and you allow, you can take the divergence inside the time derivative. Okay. Then you know that the divergence of a curl is always 0, right. Therefore, what it's saying is that the time derivative of the divergence of B is 0. Okay. So, therefore, this is not explicitly saying that the divergence of B is 0, mind you. This is how we have normally learned our electrodynamics, right. The divergence of B is always 0. This is something that's sacred. That is not what MHD is saying. It is simply saying that the time derivative of the divergence of B is 0. Okay. But if it is specified as an initial condition, in other words, if divergence of B is 0 at the beginning of your simulation, it will remain that way. Okay. That condition will not change with time. On the other hand, if you had a non-zero divergence of B due to some reason, okay, due to artificial resistivity or some problem in your simulation, then that will remain frozen as time progresses. That is what this equation is saying. Okay. Now, how about currents? This is a very interesting. So, what we do is we substitute E equals V cross B over C into Ampere's law here, right. So, this dE dt, we substitute this here. and we get that. Okay, there's no mystery. I just substitute this in here and I get this. Now, for non-relativistic speeds, in other words, for v over c much less than 1, this term is negligible, right? So, this is what I mean here. Therefore, we have j is equal to essentially curl of b. Okay, so j is essentially curl of b. How about we take its divergence? We take divergence of j, and then you know what's going to happen. I am going to take, this is just a constant, so I am going to take a divergence of the curl of b, which is saying that the divergence of j is equal to 0. So, currents also have no sources or sinks, and this is a very important statement which needs to be thought about in some detail. Okay. And this is very unlike our normal notion of currents in electrical circuits, and this is so important that we will consider it when we come back the next time. This statement, the fact that the divergence of current density is equal to 0, technically equal to 0 in magnetohydrodynamics. So, this is something that needs some thought, and so we will consider this when we meet next. For now, we will close. Thank you.